Hey, it's Dr. J. I'm back today with optimization part two. So last time we talked about optimization essentially means to find the best or the most preferred outcome. I was focused on maximizing, right? We wanted the maximum revenue or the maximum profit. Today we're going to focus on minimizing. It's the same basic process, minimization or minimizing, either way. Tomato, tomato. So we're going to talk about minimizing, and in particular, we like to minimize cost. Yeah, that's the one function in this course where it would be nice to be able to spend the least amount of money, right, to minimize our cost. Unfortunately, this is very difficult to do. Cost, generally, if you think about C and X, cost is generally rising. Yeah. Sometimes it's a straight line, sometimes it's a curve. There's lots of different models for cost, but generally speaking, it's always increasing on its domain. Yeah, and so it's kind of a bummer. Costs are always going up, right? Especially as you increase the number of units, not to mention a factor that we really haven't taken much consideration to, which is time. But generally speaking, costs go up. And so if something is constantly going up, there is no minimum value. Yeah. In order to find a minimum value, you need something like this, right? You need a shape that is decreasing, right? So its derivative is negative. We're going to use some calculus. And then on the other side, increasing. And then this spot right here would be the local minimum, or hopefully the absolute minimum in that particular example. So this is what we need in order to find a minimum. So it's going to be very difficult to just find the derivative of cost. So we start by minimizing or finding the minimum average cost. All right, and so recall average cost. Average cost is C hat, and it is the cost function divided by X. And when we do this, then this will happen, right? At least in all the examples I'm going to give you today. Right? We'll be able to find the lowest average cost or the minimum average cost. I'm just abbreviating here, minimum average cost. All right, let's get right into it. Example one, let's start with a cost function. Doesn't really matter what it's for. You can make something up. This looks like a pretty expensive cost, 67,600 plus 300x plus x squared. So it's a quadratic cost function. I'm not really going to graph these in this section, but it essentially looks like this. Right? It's a half of a parabola. I'm not really going to get into all the details. It's not an exact, not a complete half. So it's more like just this little arm of a parabola. The rest of the parabola gets cut off in the negative world. Again, I always go on way too long about that, but I always think about what the function tells you about its behavior. And in particular, in chapter 3, we are often focused on the shape of the graph. So where x represents, as usual, the number of units, produced. All right, so these units are not free. You gotta produce them. You have to manufacture them, or you have to buy them from another producer or a supplier. Again, I'm not really going to put any context on this. Just whatever object this is. So we're going to find the number of units. How about I just say find X? Find X such that the average cost is minimal. All right, so let's find X, and then what is the average cost? Find the min av cost. All right, so those are two standard questions. First, you find the X, then once you find the X, you find the actual minimum cost of whatever this particular company is producing or buying from a producer or whatever the model happens to represent. All right, let's get right into it. So average cost is the cost function, 67,600 plus 300x plus x squared, all divided by x. I usually simplify. If you don't simplify, then you have to do the quotient rule. So that's going to be 67,600 over x plus 300 plus x. Or if you prefer negative exponents, I think in the past I've done this where instead of writing over x, I just say x to the negative 1. And there is your average cost function. I often run out of space very quickly on this board, so let's go to the derivative. So next, find the derivative. This is calculus. This is the main reason why we have spent so much time on derivatives, so that this will hopefully be easy. So you've got your average cost function. Now you want to find the derivative of the average cost function. So these are all very basic rules. Multiply by the power, you get negative 67,600. X to the negative 2. Remember, you're subtracting from a negative. The derivative of 300 will just be 0. I'll write that just for your notes, in case you wonder, where'd the 300 go? All right. And then the derivative of x is just 1. And I don't show all the steps on that. Technically, it's 1 times x to the x to the 1 minus 1, which is 1 times x to the 0, which is 1 times 1, which is 1. All right. I think you should just memorize the derivative of x is just 1. All right, so now we want to find x such that the average cost is minimal. Same technique it was in the previous lecture. You're going to set c hat prime equal to 0. You set whatever derivative you took. In this case, it's average cost, derivative of average cost. I guess you could call it marginal average cost. We've used that term before. I'm just calling it minimizing average cost, which is by finding the derivative. So set that equal to 0 and solve for x. So we got negative 67,600. At this time, I like to rewrite the negative power as what it really means. Right? Negative powers are very useful when you're taking derivatives and using the rules, but when you actually get down to the nitty-gritty, get down to solving it, it's much easier to write them as positive powers. And again, I'm ignoring the plus 0, and I'm just saying 67,600 x to the negative 2 plus 1 is equal to 0. All right, and I don't really need that part right there. All right, solve this thing for x. All right, so we're going to multiply both sides by x squared. All right, remember you're distributing here. So you've got negative 6,700 or 67,600, 67600 plus x squared equals 0. Notice on the right-hand side, when you multiply by x squared, you just still get 0. But notice over here, you get x squared times 1, which is x squared. And then you get x squared times negative 6,700, or 67,600 over x squared. And so the x squareds will cancel, and you'll just get 67,600. This is now pretty easy to solve. Move the 67,600 to the other side and take the square root. And there you go. Now that you've seen the trick or the technique, you could probably solve it in less steps, because you notice that whatever x squared is equal, x squared always has to equal whatever this numerator is in order for this derivative to be 0, at least for this particular type of cost function. Not every cost function is going to be the same one. So we'll take the square root of that. Oh, I love it when that happens. Maybe it was planned. 260 units. All right. So in other words, if we order, or if we produce, or if we purchase, whatever, manufacture, whatever the word you want to use is, 260 units, then the average cost will be minimal. The graph of this one is like a rational function. So it has an asymptote. I'm not going to get into that. I just want to solve the word problem. So, all right. And again, this doesn't produce the minimal cost. It produces the minimal average cost. If you want to find the actual cost, or the actual average cost, you go all the way back to here. All right. There is no minimal cost because the cost just keeps going up and up and up and up and up. But if you plug 260 into the average, you get a number that represents the bottom, like it's a little dip in the graph. Kind of like we saw in the graphing section where the functions had this, absolute minimum, or even a relative minimum would be fine. And again, be careful. I'm not using the derivative anymore. Once you've got your x, go back to the average function, because we're finding the average, and plug it in. Oh, yeah, 260 squared. So I'm plugging it in everywhere for x. I'm plugging it into this. You could certainly use the simplified version if you like. So, or you can use this version. Maybe I should have used that version. I'll change my mind now. 67,600 over 260 plus 300. So that one will go away. Plus 260. These will be equivalent, right? This is the simplified version. This is the unsimplified version. Since I already have the simplified version, I'm just going to go ahead and use that. So, by the way, you should know this by heart. That should just be 260. If you forget that, you're going to find out real quick. You're going to go 67,600 divided by 260, and you're going to go, oh, of course it's 260, because it's the square root of 67,600. Plus 300 plus 260. So plus 300 plus another 260, and we get $820. And that's the minimum average cost. Again, this is per unit. Right? So we're basically saying if we order 260 units, right, or we produce 260 units, then our average cost is minimized to $820 per unit. Right? So that means that that's probably the size of the order we should make, right? If we want to save money, want to minimize our average cost. So there you go. That's the best we can do with minimizing, is to do the average. Not all of the functions are quite as simple as this one, but they're all the same basic recipe. Let's try one that's a little more exotic. By exotic, I mean that it has more interesting functions that might be a little more challenging, right? Although not too much. All right, same question. So we have some product. This is the cost function. At this time, if we were in the class, I would maybe pause and let you take a stab at it. I'm not going to have any dead airtime. I know my videos already go on long enough. So if you want, you could pause the video right now and go ahead and see if you can find the minimum average cost. Let's start by finding the average. This one's a little trickier because you got fractions, you've got square roots, you've got all sorts of things. Sometimes it's helpful to do this. Write the square root as a 1/2 power. And then write the divided by x as multiplied by 1/x. It's also known as the reciprocal. And that might help you. I don't know. It depends how you think about it. I don't like to see fractions within fractions, but if that doesn't bother you, then you don't necessarily need to do this. All right, so what you're going to end up with is 128x to the 1/2 minus 1. Right? When you distribute. So this is going to get distributed like this. Yeah. And then you're going to get x to the 2 minus 1 over 100. Now, I have not yet taken the derivative. I know sometimes in my lectures, people will think, oh, that -1 rule is the rule from the derivative. Well, yeah, sort of. But no, because I haven't taken a derivative. I'm just using the multiplication power rule. It is also called the power rule, by the way. It's the power rule of multiplication, though. And so when you multiply, right, this is in the denominator. This is x to the 1 in the denominator. You subtract the powers. Don't worry, I'll be doing the derivative rule in just a minute. As soon as I put a prime, then you know I've used the derivative rule. Oftentimes, this is all done mental math. So I just do that mentally. And you're going to get x to the negative 1/2 plus x to the 1 over 100. And that is our average cost function. Save that for later. All right, save that for later. We're going to need it. So I'll just write the word save me up here to remind me that if I do go to erase this, I want you to yell out at your monitor and say, stop, you got to go back and save this. All right, next we're going to find the derivative. So this is the derivative of the average cost. All right, marginal average cost, I guess. That's what we called it before. Although I'm not going to be asking for that this time. I'm just asking for the minimum. So you can just call it the derivative of average cost. We're setting it equal to 0. So let's first find the derivative. Now I'm going to do the derivative power rule. So multiply. So that'll be negative 64 x to the negative 3/2. All right, remember, you multiply the power times the coefficient. That'll give you negative 64. Then you subtract 1 from the power. So that gives you negative 3/2. And then remember, this is just the same as 1 over 100 times x. So the derivative is just 1 over 100. Or if you prefer, 1 cent. That's what that means. 1 over 100 is 1 cent. So it's like having 1 additional cent at the end of your average cost function. And then set this equal to 0 and solve. All right, here's where I erase and I go, stop, save me. C hat is 128x to the negative 1/2 plus x over 100. All right, I saved it. I'm not using it right now. It's just being saved. All right, so we're saving that. Let's get back to our derivatives. So now we have negative 64 x to the negative 3 halves plus 1 over 100. You know what? I actually prefer writing it as 1 cent. Yeah, and then equals to 0. It's just cleaner. If you get a nice decimal, this is business math. It's really useful to see it as 1 cent. Right? It might come in handy when we're calculating the dollar amount later. I also like to see this as what it really is. So it really means negative 64 over the square root of x cubed. That's what negative 3 halves actually means in math language. And this is really no harder than the last one. It's just instead of a 1, in the last one we had a 1 here, it's 1 cent, right? And then instead of an x squared, we've got the square root of x cubed. But it's the same basic principle. Same basic principle. In order for this to equal 0, this must equal negative 1 cent. Or you could multiply both sides by negative 1 and just say this, 64 over the square root of x cubed equals positive 1 cent. And I hope intuitively that makes sense, because if this equals negative 1 cent, then you have negative 1 cent plus 1 cent would equal 0, right? And then by ignoring the negatives, or by multiplying by negative 1, oh, that doesn't look very nice. Let's try that again. Negative 1 with a parenthesis there. By multiplying both sides by negative 1, now you have a much easier problem to solve, which is the positive version of the same equation here. Right? You could certainly tease this out into several steps if you wanted, but I'm really trying to cut to the chase here, since I can, okay? And you can too. All right, we got to get x by itself, so let's multiply both sides by the square root of x cubed. All right, that'll cancel on this side. So we'll have 64 equals 0.01 times the square root of x cubed. Let's divide both sides by 1 cent. So we've got the square root of x cubed is equal to whatever this is. It's going to be 6,400. Let's see, 64 divided by 1 cent. Yeah, 6,400, or 6,400 in another language. I did switch sides. I just switch sides so that my x is on the left, just for convenience. Okay, so I did a little flipperoo here. And then now let's square both sides. That gets rid of the square root. And then let's take the cube root of both sides, and that gets rid of the cubed. And here's a little fun fact if you've not taken algebra in a while, if it's been a while for you. When you have a root and a power in the same expression, right, as long as there's no adding or subtracting involved, if it's just multiplication or division, you can do them in any order you like. The order of operations, I know there's this order of operations you're supposed to follow, but In this particular example, that order of operations is equivalent. You could do them in either order and you will get the same result. If you don't believe me, try it. So first do the cube root of 6,400. You get this big ugly decimal, 18, who you calling ugly, right? 18.5656, whatever. 5663, blah, 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 blah. And then square that. I'm just going to keep that on my calculator and hit my squared button. Oh, you're screaming at me right now, aren't you? You're going, Dr. Jordan, you screwed it up. Look. Oh, no, I didn't. No. I did it right. It's... I almost screamed at myself. It was cubed, but it became a cube root, right? And then it was square root, and then the square root became squared. So I was looking at these powers and thinking I had them backwards, right? I don't. I mean, they are backwards now. They're backwards because I've isolated the x. So it's no big deal. We're fine. We did it. I don't want to have to redo this one. And there's your final answer, 344.7, or approximately 345 units. Typically, you round to the nearest whole number. Now, you could argue, well, when you buy that extra unit, you're going to go, above your minimum. Sure, yeah, you could argue that. So you could say, you should probably just order 344. But this is a computer that's taking your answer, and so just do what the computer likes, which is rounding. So round it to 345. But if you're, talking with a person about it, you could certainly debate whether you should do 345 or whether you should do 344. You can't order 0.7 of something, right? You have to order a whole object. So again, that's a human debate that I will leave for the humans. For the computers, just do what it asks you to do, which is to round. So 345 units. All right, there you go. Not too shabby. So again, this number of units would represent that dip in the average cost function. And I saved my average cost function up here. So now I can find the minimum average cost by plugging in 345. 128, 145 to the negative 1/2 plus, 345. 345 over 100. Which really means the same thing as 128 over the square root of 345 plus 3.45. Right? Translate this into numbers. So square root of 345. I'm going to do this all at once. So square root, and then I'm going to do, here's a little trick. I don't know if I've shown you this before. If you've already done the denominator of something and you don't want to write it down, you can just hit the 1 over x button. It's right over here on the side, 1 over x. And that will send it down to the denominator. But then you don't divide, you multiply by the top. That's a quick way to do division without having to rewrite it. So you get $6.89 plus $3.45. And so that's going to be, now this is rounded, obviously, so I'm going to say approximately. So we're going to add 345, and we're going to get $10.34. And this is now money. So that is your minimum average cost per unit, of course. It's not $10.34 to order this many units, right? If you want to know how much it costs to order this many units or to produce this many units, You got to go back to the very beginning of the problem before we did the average, before we did the derivative, and plug in 345. We did that in a previous chapter, right? That's just called finding the cost, right? It's a lot of money, trust me, right? But this tells you how much money it is per unit, right? Although I guess you could figure if it's $10 per unit and you're ordering 345 units, it's going to be about $3,450, right? About approximately. There's this extra money here. All right, so that's minimum average cost. Done. I only have 2 examples today. You could, in theory, take any of the cost functions that we've learned about in this course and apply this technique to any of them. Right? I just picked 2 of the more interesting ones. And since this is the end of the chapter, the end of the optimization generally, I just want to move on to something else. So there are 2 things that you can find the actual average, the minimum average, without finding the average. The minimum cost without using average cost. There are a couple things. Production cost. So this is minimizing the actual cost to produce the units, not by taking an average. And I'm only going to do 2 different things. These are the 2 most common ones. They're, in fact, the only 2 that I could find. Inventory cost. Although there is a 3rd one I found, labor cost, the cost of human labor. But that's a more complicated problem. It actually requires more calculus than we know at this point. It turns out once you involve humans and working, although I might have talked a little bit about it. I did a very rudimentary example, but I'm going to keep it to what we actually have the techniques today to be able to solve. So we can solve these 2 problems, production cost and inventory cost, without using an average, right? Just by using the actual cost of whatever it is that we're producing. My battery's about to die. I don't want to. I have had the battery die in the middle of a video before, and it's a real hassle. I have to splice, All right, but we don't use scissors anymore for splicing. Let's do it all on the computer. All right, let's go ahead and do it. Let's start with production cost. So for production cost, here, let me erase this. It's taking up too much space. Example 3, production cost of a box. Real simple geometric shape, a box. So we're going to produce a box, and it's an open top box. It turns out to include the top is essentially like making another box, right? So I don't know. It depends what type of box you're making, but this is an open top box. So it essentially looks like this. Rectangular box. Yeah. The top is open, so there's no lid. Right? But the bottom of the box is reinforced. So we have a reinforced bottom here. And let me put a little dotted line here for the back corner. And so the bottom costs more. It's stronger material. Than the sides. So I tried to do a little bit of, my own personal experience and then doing a little investigating of what types of things use these kinds of boxes. They're used a lot in agriculture. So you'll have like a back of a truck with a whole bunch of these boxes on it. They got a reinforced bottom so that when they put the produce or whatever in and then they go to move it, they want the lid to be open. They don't want a lid because they want to be able to dump, whatever goes in there, the apples or the vegetables or whatever it is that you're harvesting. But the bottom has to be reinforced because when they go to lift it up, they don't want the whole bottom of the box to break out from underneath it. So that's one example of why you would make an open top box like this with a reinforced bottom. Another example would be like in the post office. They have these open top boxes, although they're not perfect rectangular like this. They're a little bit kind of angular. They kind of look like this. You might have seen them. Maybe you work in an office, right? This is also more complicated. So I keep it simple, make it rectangular. But like in the post office, they use these open top boxes like this. The bottom is reinforced. It's extra strong so it doesn't break when you put all the mail in it. So anything like that, where you want to have easy access, you want to dump things into the top of the box, and you don't want a lid, right? Okay. So enough of my justifying why we're making an open top box. Our goal is to find the cost function. All right. The sides cost, how much does this box cost? 3 cents, not 3 cents, 0.3 cents, 0.03 cents. I want to point out this is less than 1 cent. This is 3/100ths of 1 cent. Right? It is not 3 cents. This actually screwed me up the first time I read this problem because when you read it very quickly, you think that says 3 cents. All right. I want to note that if I say this, so I'll just say note, just note to, human understanding. When you say 0.03 dollars, this means 3 cents. You have to say 0.03 dollars, and if you actually mean 3 cents. This, although it looks like 3 cents, means 3/100ths of 1 cent, which is very, very cheap. Right? It's less than a penny per square inch. Am I doing inches or feet? Inch per square inch. And the bottom is more expensive. The cost for the bottom is 0.12 of a cent per square inch. All right. Or I could say per inch squared. This means the same thing as this. All right. Now notice the bottom is more expensive. That's our bottom there. That's going to cost more. It's going to cost more. All right. And so find the cost function. Yeah. And I will give you the costs for the side and the bottom. All right. So this time we are making a box. All right. The volume must be given. In this problem, we want, so I have to give you how much, what's the volume of apples or the volume of, avocados or lettuce or whatever that's going to fit in there, or mail. 16,000 cubic inches. So this must be given in the problem. Otherwise, we can't do it. All right, let's do it. Now we have a box. All right. Remember, volume is length times width times height. That's called volume. All right. Now, Let's save this for later. So let's just put save 0.03 for the sides and 0.12 for the bottom. That's all we really need to know is how much these are going to cost. Yeah, it's per square inch, but that's all going to work out in the end because we're going to do the cubic inches. So that's the total volume, length times width times height. All right, so let's suppose that we just look at the bottom. All right. Now the bottom, we'll call it, say, X. And we have to pick a side to be X. Now, for this example, I want the bottom to be a square. So even though I drew it as a rectangle, I'm going to adjust my drawing a little bit, and I'm going to say a square bottom. God, that doesn't look very much like a square. Let me draw it like a square. There we go. If this is X, then this is also X. Yeah. So if the bottom is a square, this is the easiest case. So I'm going to do the easy case today. All right. And I don't know if we'll have time to do the more complicated case. The more complicated case would be where the bottom is not a square, and it does get extremely more complicated at that point. So for now, since I'm already 40 minutes into this lecture, I'm going to do the easy case, which is the bottom is a square. Now that's going to be your length and your width. Yeah, so you got your length and your width. So now the volume is X times H. So I'm saying, L is equal to X and W is equal to X. I'm just forcing the length and the width to both be the same so that I can solve the simple case. Case 1. That it's a square. All right. And then I know that the volume is 16,000 cubic inches. So 16,000 becomes my V. X times X is X squared. And then now this gives me an equation for H. Just divide both sides by X squared, and you get 16,000 over X squared. Right? Here, let me show that. Divide both sides by X squared. Cancel, and get H all by itself. So H will be equal to 16,000 over X squared. Case 1. All right. Now, I will be able to plug that into here, right? But remember, we're building the box, right? We're not filling it yet. The volume is actually what goes inside the box after you've built it. To build a box, you need the surface area. Right? All of those sides and the bottom have a surface area. So the area of the bottom is X squared. So the area, it's a function of X, is the area of the bottom plus the area of the four sides. Okay. Now, I don't know if you remember my old picture. I'm going to redraw my old picture here. This time I'm trying to make it look more like a square box. Although it's not really a cube, because the height is not the same as the x. So the height is h. Right? But all of the sides are x, but the heights are all h. Yeah, so this is x, all the way around it's x, but the height, these guys, I want to color them in red, are all h's. Yeah. Now remember, there are 4 sides. You can only see 2 of them, but there are 4 of them. All right. Each side has an area x times h. So the area of the bottom is x squared, but the area of one of the sides is xh, or x times h. That's just one side. You with me? All right. Now, by the way, once I do this, and I'm really dragging this on, I know. As soon as I write down the formula, you're going to go, well, shit, I could have just solved it from there. Shoot, I should have just solved it from there. I don't know. Do I have any kids in my calculus class? I don't know. All right, so we got the area of the bottom. Sometimes people use the letter S for surface area, or SA. I'm just using A. Okay. Area of the bottom, which is x squared, plus 4 times the area of each side, 4xh. Because the area of each side is xh. And I don't really need the dot. It's just 4xh. All right. There we go. And now, the cost. Oh, no, we're not ready for cost yet. One more thing. I got to get rid of h. What was h? I just erased it. It was 16,000 divided by x squared. Remember? I had already solved for h. So I have to replace h with 16,000 over x squared. And now we're ready for costs. So let's write this down one more time. That's going to be 64,000, 4 times 16,000. And then I'm going to cancel one of the x's and just say over x. All right. Now we're ready for cost. So multiply by each cost. And you have to do it in the right place. So the x squared is the bottom. So 0.12 x squared. So the cost of the bottom is per square inch. So that's your square inches for the bottom. It's interesting that the sides no longer have the square on it, but I mean they did. They did a minute ago. We just simplified it. So this still represents the sides, the square inches of the sides, and then multiply that by 0.3. 0.03, and that's our cost function. So all of that work was because we didn't have a cost function. 64,000. Remember, it used to be 16,000. Then I multiplied it by 4 and got 64,000. Now I'm multiplying it by 3/100ths of a cent. So that's going to become 1920. And after all of that work, you're going to be like, I hope he just gives us the cost function. So in the first 2 examples that I did today, I just gave you the cost function, but I had to show you at least the simple case. All right. Again, this is case 1, square base. Or square bottom. Case 2 is a little tougher. I will not have time to do the non-square base today. Or I don't know if we're ever going to be able to do that. I'll have to think about it. if I do come up with a solution for the case 2 that is within the scope of what we've learned already, I'll certainly report back to you. But for now, we're done. All right. So once you have the cost function, it's all downhill from there, right? I hope everybody realizes after all these weeks watching these videos that once you actually have a function in your hands, the calculus is not the hard part, right? The hard part is analyzing, applying, reading and making sure that everything is, up to snuff. Now, this is not average cost. This is just cost. Yeah. And so we're not going to do the average cost. We're just going to find the minimum cost. We don't need an average because this function does have its own minimum. Doesn't require that we take an average. So we just take the derivative. Remember the rule, you multiply. So it's going to be 0.24x. And then that's going to change to a minus. I hope you all remember the rule, 1920. And that'll be x to the negative 2. If you don't remember the rule, I'll do a quick reminder here. That's 1920 x to the negative 1. You multiply by negative 1, so that becomes negative 1920. And then you subtract 1, and that's how you get negative 2. Just a quick refresher of the power rule for negative exponents. And there you go. You're basically done. So C prime of x is 24 cents times x minus $1,920. Those are now dollars now. This is 24 hundredths of a cent. So it's almost a quarter of a penny. If you took a penny and cut it into 4 little tiny quarter pennies, then that's what that represents. It's a little bit less. 0.25 would be a quarter of a penny. Right? Like maybe in the old days where a penny actually bought you something. You could have something that costs a quarter of a penny. I don't know how you would cut up your pennies though. I think they used to have half pennies. You could do a little historical research. They used to actually make a penny that was worth half a penny. It was worth half a cent. Can't find them anymore. And someday there'll be no more pennies either. Canada already got rid of their pennies. All right, anyway, so this is your cost function. Now you want to set it equal to 0 and solve for x. So you got 24 cents times x minus 1920 over x squared is equal to 0. There are lots of different ways to solve this. Let's do the multiplying by x squared method. I like that method. So multiply everybody by x squared. Make sure you hit everybody. All right. So that gives you multiply by x squared. I almost wrote x cubed. I'm jumping ahead. So this will become x cubed now. 0.24 x cubed. These guys will just cancel. You get 1920. And that, when you multiply this side, you don't change it. It's just 0. So you might ask, well, why do I have to do that side if it's just going to become 0? Because it's math, right? And whatever you do to one side of an equation, you got to do the same thing to the other side. So I'm just exercising good math here, even though the right side didn't really matter. Move the 1920 over. You're going to get 24 hundredths of a cent times x cubed equals positive 1920. I'm adding it to the other side. So again, I want to save that. I'm going to need it at the end. 0.24 x cubed equals 1920. Just rewriting it up here so you can see it. Divide by 24 cents. At this point, I'm just talking to myself. You already know how to do this. This is just solving for x. 1920 divided by 24 cents is 8,000. That's nice. I'm always really happy when that happens. And then I'm going to take the cube root of both sides. So I'm going to get the cube root of 8,000 is 20, I think. Yep. 20. Very nice. I tried to make the problems because the setup is intense. I tried to make it that the other side after you've set it all up should be very nice. Right? So you get kind of a nice kickback after doing all that work. All right, so this is 20, what was it, inches, right? That's the length of the side. That's the length of the base. And the width, actually, because it was a square. What's the height? The height is h. That was what was it again? 16,000 over x squared. So that would be 16,000 over 400. I'm doing the mental math here. 20 squared is 400. And so that's exactly 400, I think. No. 40? 40. Why am I even breaking out my calculator? You know it's 40. 16,000 divided by 400. Of course it's 40. I just wanted to make sure, all right? It's late. All right, that's the height. All right. You can check the volume to make sure your box holds what it's supposed to hold. X times X, so that's the length and the width. They're the same, right? And then the height. I don't even know why I'm bothering wasting your time. Of course it's right. 20 times 20 times 40 is 16,000, which is originally what it was supposed to hold. And then now to pay for this material, you could check the cost. Just plug in 20. And again, this is not average cost. Although, yeah, it's not average cost. This is the cost to build one box. If you build two boxes, because we're not doing an average, if you build two boxes, well, you're going to double this. If you build three boxes, you're going to triple this. This is the cost, the actual cost. All right, to build one of these boxes. And this is in cents. I'll point that. This is in cents. I think. Yeah, this is in cents. Yeah, this is in cents. Because that's not, $0.12. That's 0.12 cents. So 20 squared, 400 times 12 cents is 48 cents, right? And then 1920 divided by 20 is 96. So plus 48, 144 cents to build one box. Or you could say $1.44. That was rough. I don't know if we're going to have time for inventory cost. But we have to, because this is the end, my friends. All right, so inventory cost. It is very similar to, so I'm done with the simple box problem. It was tough at the beginning. There was a lot of setup, but getting the final answer was not so bad. All right. You do have to really pay attention to what you're measuring, right? You're measuring in cents, but anyway. For the next one, I'm going to measure in dollars. It makes it a lot easier when you measure things with dollars. Oh, I should mention that's a pretty cheap box. Yeah. Although it wasn't really very, 20 inches. So it's less than 2 feet. It's a pretty small box. All right. The last thing, inventory cost. We haven't really talked much about inventory. I don't think we've talked about it at all. Inventory cost. So the inventory cost is the cost of your inventory, the stuff that you have in, the supply area. Let me just go ahead and give you the example. And there are two of these that you're going to have to do. One of them, I just give you the formula, right? But I think I've done enough of that, right? I think, you already kind of saw that if you already have the formula for cost, you just do it. You just take the derivative, set it to 0, solve for x. So I'm going to focus, because we only have about 20 minutes left, I hope I can get it done quicker than that, on how to find the formula and explain the inventory cost formula. So a retailer sells, I don't know, what do you want to sell? Shoes. All right. They purchase the shoes in lots. All right, lots. It's a big lot. It's an order of a bunch of pairs of shoes. It costs $8 to store them for 1 year. All right, $8 to store a pair of shoes for 1 year. So it's kind of like thinking of, your inventory is all of these boxes of shoes, right? I'm only drawing dots instead of boxes, right? And you've got them in, a warehouse somewhere, right? And you got to pay people. You've got to have the air conditioning, although I guess the shoes need to be air conditioned. I don't know. But these costs are what it costs to keep all of these shoes in your storage. All right, it's not free, right? And again, it's based on the square footage. It's based on the size of the box. So I'm going to give you that number. All right. So it's $8 to store the shoes for a year. To reorder more shoes, there's a fixed fee of $20 per lot. By the way, a lot is just a fancy way of saying an order of more than one pair. Although I guess there's no rule that says it has to be more than one pair, but come on, be realistic. You're not just going to order one pair of shoes if you're selling shoes, right? Plus you're paying $20 just to order it. Plus $4 per pair. You see how, so you're sort of incentivized to order more shoes because once you pay the per lot fee, obviously if you're only ordering one pair, it would be $24. If you're ordering 2 pairs, it would be $28, and so on and so forth. All right. Find a function that models the inventory cost. Inventory costs. Cost? Yeah. As a function of X, the lot size of each order. All right. So you don't have to order the same amount every time. You can say, X is the lot size. So I'm going to order 100 shoes this week. I'm going to order 20 pairs next week. It's going to be a variable. So I'll have an X. So I want to find C of X. All right. So it models the cost of inventory. How much it costs to have all these shoes in my storage. All right, let's do it. It's a lot like the box problem. We're going to have to oversimplify it and think about what that cost is. So cost is the number of orders per year I'm assuming that we're just doing this annually, right? Because everything was given in terms of a year. Times the cost of each order. Yeah. Or the cost of each lot. A lot is just an order. Plus the storage cost. All right. Put parentheses around that too. All right. So let's think about this for a minute. Oh, I forgot to tell you. There's one important thing. Oh, given, I'll put it down here in the problem. Given that they sell, I got to tell you this, 4,400 pairs of shoes each year. Oh, I almost blew that one up, because as soon as I erase all this, I would have never thought to go back and do that. So this is super important. I got to know how much they're selling. That's going to tell me, how many pairs of shoes I'm going to need to keep in my storage, right? It's important that I know that. If I don't sell very many shoes, I don't need a lot of shoes in storage. And that's the worst diagram I think I've ever drawn. Each dot is a pair of shoes, right? A box, I guess, with two shoes in a box. All right. So the number of orders per year. Oh, I don't want to lose this. I won't lose it. So the number of orders per year, that's the total number that they sell in a year divided by X. All right? Because X is the size of each order. So for example, if I only order, a real simple example, if I only order one pair of shoes at a time, 4,400 divided by 1 means I have to place 4,400 orders that year. That's pretty stupid, right? Not very smart. Suppose I order, 10 pairs of shoes in every order, every lot. Well, then 4,400 divided by 10 would be 440. So if there was 10 pairs of shoes in every order, then I would have to place 440 orders. Let's do one more silly example. 100 pairs of shoes. Now we're talking. 100 pairs of shoes in a truck, right? 100 pairs of shoes, 4,400 divided by 100. I still have to place 44 orders per year if every lot has 100 pairs of shoes. And X can be different, right? It doesn't always have to be 100. It doesn't always have to be 10. Our goal is to find the optimal order. We want to find the best amount. All right, now the cost of each order, that was given in the problem. The cost of each order is given. $20 per pair plus $20 per lot plus $4 per pair. So that's 20 plus 4x. All right, now I don't need any of this. All right, and then I'm going to get rid of this. That's going to go right here. It's $8 to store a pair of shoes for a year. Now, I'm going to admit to you, this is where I, as a student, and honestly, even as a professor, if I just went into this cold, right, without any preparation, even with all my training and experience, I probably would have just put 8 right there. And I want to admit, the first time I did this problem, that's exactly what I did. Because the storage cost, I'm thinking, is $8, and that's it, right? It's only $8 to store a pair for a year, right? But it's not. It's $8 for each pair of shoes, right? So how many pairs of shoes do we have? How many pairs of shoes do we have? Well, this is where we have to make an assumption. This is kind of like the box problem, where I assumed it was a square. So we are going to make this assumption, and you can make the same assumption when you do this problem. Assume that the inventory is only 50% full at any given time. Now, I've heard lots of arguments for why this assumption is reasonable. Well, you can think of the course of the year, right? It can go from being empty, right? 0 pairs, 0%. Oh my God, we don't have any shoes, right? That's not very realistic, but it could happen, right? You could sell all your shoes and have to wait for another order. Or you could have just gotten an order, right? And had 100%, right? So the amount of shoes ranges between 0 and 100%, right? And so we take the average is 0 plus 100 divided by 2, and that's how we get 50%. So 50% is the average number of shoes that's in the storage at any given time. So our storage cost is $8 times X over 2. In other words, half the shoes, or X is the number that the shoes that we've ordered, right, in the lot, half of them will remain in storage for a year. So average of half of each order or each lot remains in storage. You could say 50% or you could say X over 2. This just means 50% of X. X over 2. And there you go. That's it. That's your cost function. Just in the nick of time, because I'm sure you're probably getting sick of me. So now we have the cost function 4,400 over X times 20 plus 4X plus 8 over X over 2. 8 times X over 2. Simplify this. Calculator is handy. I don't really need it. 88,000 over X. 44 times 4. Oh, God, I'm tired. Maybe you could do that for me. I did that one in my head. I'm not feeling like doing that one. 4,400 times 4. 17,600. Now notice when this hits this term, there's an X on top and X on the bottom. This one no longer has an X. And then here, 8 times X over 2 is 4X. So this is our cost function. Yay! And I think in one of the problems, this is all given for you, and you could start the problem right here. All right. But in one of the other problems, you actually have to construct this. I don't know if they're going to be shoes. They don't have to be shoes. I think I've seen one problem where it's like they're storing frozen food. I kind of like that version. Frozen food to me makes more sense because you got to keep it cold, right? And when you got to keep it cold, the cost of storage becomes a little bit more, I think, understandable. I don't know why I picked shoes. I don't know. I'm thinking about shoes today. Maybe I need a new pair of shoes. All right. So the whole lesson is minimizing. So now find X such that C cost is minimal. That is the whole lesson today. So we're going to do C prime of X. Here's our C. I'm going to do this very quickly. It's negative 88,000 over X squared plus 0. I'm not even going to write that down, right? The derivative of this constant goes away. And then the derivative of 4X is plus 4. There we go. Boom. So there's your derivative. All right. And then we're going to set this equal to 0. 88,000 over X squared plus 4 equals 0. And just like all the other problems, we're going to solve for X. Can I skip a couple steps here? Can I just say 88,000 over x squared has to equal 4? If you like, you could say I'm moving the 4 to the other side. It becomes -4. And then I'm multiplying both sides by -1. In the interest of time, the bell's about to ring. There's no bell. That's the thing. It's the same thing every single time. Or you could say x squared is 88,000 divided by 4. Just switch the 4 and the x squared. Or you could say x squared is 22,000. 88, I feel stupid doing this, divided by 4. Just want to be safe. It's been a long lecture. And then take the square root of both sides. So you're going to get x is 148. You do have to round. So 148. I was really hoping for a better number. I sure hope I didn't make a mistake because it's too late to go back now. $148 pairs of shoes. There we go. Well, that's it. So 148 pairs per lot. Yeah, or per order. That's a lot of shoes. Get it? Dun-dun-dun. I'll be here all week, folks. So you're going to order 148 pairs in each lot, and then that will minimize your storage cost. You could go, I'm not going to do it now, but you could go through it and figure, okay, if you're going to sell 44,000 or was it 4,400 pairs of shoes every year, how many orders do you have to make if you make the same order each time, same size order? Now you get to choose small, medium, or whatever the shoe sizes are, 9s, 10s, 6s, kids, whatever. But we're assuming it's all equal. The storage cost is the same for grown-up shoes as kids' shoes. Maybe that doesn't make sense either, but hey, maybe the boxes are the same size or whatever. And then finally, the minimum cost. The minimum annual, this is for 1 year, inventory cost is C, not the derivative, but just the regular C of 148 pairs of shoes. So that's 88,000 over 148 plus 17,600 plus 4 times 148. This seems like a lot of money. Yeah, it seems like way too much, but I don't know. I'll issue a retraction if I made any mistakes, but for now, let's just figure it out what we've got. So you're going to get $5.94. I better keep the change, 59 cents, plus 17,600. This is expensive business. Plus 17,600, which was 4,400 times. Yeah, that's 17,000, isn't it? Whew, this is expensive. Plus, I forgot to write that down. 18,194 and 59 cents plus. I forgot to do this one. So what's that? 4 times $148 is $592 for a grand total of a lot. $18,194.59 plus $592. Now the grand total is $19,378 That doesn't make sense. Something's wrong. Let's try that again. $18,194.59 plus $592. There we go. A grand total of $18,786.59. Put a dollar sign in front of it. Whew! We did it. Or I did it. You watched. Hope you enjoyed yourself. We are done with chapter 3. If there are any mistakes, you notice any mistakes, feel free to email me. I will give it a second look and issue any necessary corrections or retractions. But that was your lesson for the day. Until we meet again, I'm Dr. Jordan, and I'll see you on the internet.